Okay, so the question was, what does an engineer do?
Right.
And the answer to that question is they solve problems. Now that's the traditional way of describing what an engineer does. I like to turn that whole sentence around, and I like to call them solution providers.
Solution providers.
Yes, that's what we do. We provide solutions to problems. In some cases, maybe there isn't a problem. Maybe there's just a need,
Right.
or maybe there's an advantage.
Right.
In those particular situations, we might call it value added.
Value add.
We add value. So what the engineer does is, if I look at it from, that 20,000 foot level looking down on the earth, okay, what I see them doing is adding value,
Right.
right? Providing solutions. If you want to call that solving problems, well, you can do that. Now, how do we do that? Well, it is a discipline. It takes a lot of study, and the application of all the things that we study, we put together so that we can actually use it to solve a problem.
Study as in like making thesis or like reading kind of study?
Well, you got to have the tools in order to be able to solve some of these problems. These are not simple problems. The problems that I see as an engineer are problems that other people walk away from.
Right.
Most people, when they see a problem, they turn around and they go the other direction. When an engineer sees a problem, they see a paycheck.
Right.
So, like I said, these are not going to be simple. If they were simple, somebody else would have done it, and they wouldn't have needed an engineer to come in and try to work on that solution. Good technicians make good engineers. So before you become an engineer, I recommend that every engineer work sometime as a technician. They're going to find that that's very valuable.
Right.
The things that we see as a technician, we don't get to see as an engineer because of the other side. Besides the practical application of the theories, there is those theories that as academics that need to be studied. And so I began my career as a student, as a mathematics student. So I was a math major.
Math, sure.
And then when I got through most of the math, you take the physics next. So now you get to see that you get to do something with this math. And so that thing we get to do is physics. But once again, it's still all theoretical. The math was theoretical. The physics was theoretical. It was all theoretical, right?
Correct.
But there were some engineering students in my class.
Right.
And I went to a polytechnic. And the philosophy of polytechnic is that what you study, we then apply. So we had a lot of word problems. But, still as a math major, it was mostly, theoretical, academic. They give us a problem. There is a solution to the problem.
Yeah.
We work through it. A lot of the problem was more understanding what the question was asking than it was trying to figure out what techniques in mathematics I need to apply to arrive at the solution.
Right.
Physics was kind of the same way. But like I said, there were some engineering students in the class. And they were telling me about the things that they were doing.
Like?
And so for them, math and physics was a tool that they used to apply towards engineering methods and engineering disciplines. So this was a tool. Working as a technician, I began to see the math and the physics as tools like screwdrivers and wrenches and hammers and saws, and they could tear things apart. I could put things together. Yes. And the math and the physics lets me do that. But working as an engineer, you then have to select which discipline it is that you want to get involved in. And there are many. I mean, if you said, I want to be a mechanical engineer, well, then we got this list to choose from. Do you want to study statics, which is structures that don't move? Do you want to study dynamics, which are things that do move?
Right.
Do you want to study, in the things that do move, do you want to study hydraulics,
Right.
or pneumatics,
Right.
or gears,
Right.
or levers, or the list goes on and on. What do you want to study? Now, I studied electronics, and oh my gosh, that field is really big, really, really big.
Right.
So, my first job as a technician, I took on as a, I think it was a junior.
Okay.
And I just finished a whole lot of engineering courses, and I was asking myself, do I know how to do this? Do I want to do this? What is this? I was asking myself the same question you're asking. What does an engineer do? So
Right.
I went looking through the want ads, and I found a job for a technician. Wasn't even they had another job opening there for an assembler. And so I'm thinking, I'm going to go to work for this company for the summer, and I'm just going to screw parts together, and I'm going to watch the factory and see how it all works. I'm going to talk to as many engineers as I can. I'm going to get to
Yes.
know all the technicians, and I'm going to go pick a subject that I really hate.
That is.
There's a machine that I cannot get to work. Now, you have to understand, right? I was a pretty good mechanic.
Right. Yeah, in
Okay.
which in layman language, I guess it's called like fixing stuff and all.
Fixing things, yeah. Okay, so like I could rebuild the car, the engine, the
Okay.
transmission, right, the brakes. I could do the whole thing. Right?
Again, mechanical.
Yeah, I could do computers. I could put them together. I could tear them apart. Right, I could do that. Right, but the printer, oh my God, the printer was my nemesis. And so I found a company local that makes printers. This is what they do. And I said, I'm going to go to work for them, and I don't care what role they give me. I don't care if I have to sweep the floor. And so I went over there, and they gave me a test.
Okay.
And I sat there in the lobby, and I
Oh.
took this test.
How was that?
It was long.
It was long.
It was the comprehensive final exam for every class I had ever taken up until the end of my junior year. Every class,
Mm-hmm.
every single class was in that test.
Okay.
And so I sat there and I started, the test was thick. It was like, it had to be close to, I'm not exaggerating, 50 pages.
Uh-huh.
And so I'm looking at these questions. It was just one
Wow.
question after another. There's not enough room on the test to calculate the answers.
Yeah.
So you have to ask them for extra paper.
Right.
And so I'm sitting there, and they said, take as long as you want, do as much as you can, and let us know when you're through. And so I took the test.
Your experience
This is like 9 o'clock in the morning, right?
Okay.
At 3 o'clock, I turned it in.
Okay, that means it's too much reading and preparation.
So the girl that took the test from me, she said, "You did the whole thing." And I said, "Well, yeah, you told me I had to take my time and do as much as I can." And
Right.
I knew all this stuff because I've studied all this at school. Where do you go to school?
Okay.
I go to school at Cal Poly.
Cal Poly.
She said, "Wait a minute, I'm going to have to go get the engineer." So the engineer comes back out there, right? And he says, he's looking through the test, right?
Mhm.
He says, "You got them all right." He said, "You did the whole thing."
Right.
And he's turning the pages and he's looking at it, right? And I said, the advantage was, I think there was one I might have made a mistake on. I said, but the advantage was you told me to take my time. And so I did.
Right.
And so I checked all my work, and I think I got them all right but one. And as it turned out, I got that one right too. But he said, "What do you want to do?" And I said, I know nothing
Mm-hmm.
about being an engineer or a technician,
Right.
but I can put pieces together. And if you could just give me a job on the assembly line, I'll put pieces together for you.
Right.
And he says, "No," he says, "I think we're going to put you in production test."
Okay.
And so you'll get to meet the other guys there, and they'll show you how to test the machines and the circuits, boards that we build. And he says, and we'll start you off there. And so that was my first exposure.
The production test.
Production test, yeah.
That's cool. Production.
This is going way back, right? Okay, so
Right.
way back.
That's
All right, so at that time, the microprocessor was brand new.
Okay.
Brand new, right?
Fine.
There weren't a lot of people that knew how to use it.
Got it.
And mostly it was the graduates that were just coming out of college that knew
Mhm.
how to use this processor.
Yeah.
And so I looked at the circuit board that they made, and the guys are showing me all this equipment that they've got, and most of it I'm familiar with. Test equipment I used at school,
Right.
and so they said, okay, so here's a board, here's a circuit board. It runs the printer, all right.
Right.
It just came off the assembly line, tested. Somebody has already tested
Okay.
it. It's tested, right?
Uh-huh.
And they saw a flaw.
Okay.
You verify that it is got a flaw,
Okay.
and then you fix it.
Fix it if
Mhm.
it has a flaw.
Yeah, they said verify the flaw and then fix the flaw, whatever's wrong with it. And so and they showed me how to run the little test, right?
Right.
And so I did. It's basically just a calculator. That's what it
Okay.
was. And so I did one, and they said, now study the circuit, make sure you understand it. And so I studied the circuit, and then they said, okay, it's time for break. And I'm thinking, oh, this is fun. This is easy, right?
Yeah.
Right. And so after break, they told me, okay, so now fix these 5 that you found problems with, and then call me when you're done. And so they brought them out in a little tray, right?
Okay.
And these things are standing up like I don't know, like donuts on a cookie tray, right,
Okay.
or something. And I looked at these boards. I fixed them, and then I went and I said, okay, I'm done. All right, you got any more?
Yes.
What do you want me to do now?
Yes.
And they said, oh, good. They said, all right, so come with me. And so I followed the supervisor,
Mm-hmm.
and she took me over to this area set aside in the production, where she had these racks. They were like 6 feet tall,
Right.
and they had shelves on them. They were 2 feet by 2 feet by 2 feet
Right.
square, and the shelves were about 10 inches apart, and all of these are filled with these circuit boards. And
Okay.
these are all boards coming out of test
Test.
on the production line,
Mm-hmm.
and they've all failed.
They've all failed.
They've all failed.
Okay. So you had to fix them.
Yes, there had to be 300-400 of these.
Okay.
And I'm thinking, oh my gosh.
Seriously?
So I rolled the cart back to my station, and I sat there and I started testing these boards, and very quickly I began to realize there were some patterns.
Aha.
They put a part in backwards.
Okay.
And so I made a note of that. There was another, it was the wrong part,
Okay.
and there was a whole batch of those.
Mm-hmm.
And then there was some other ones where when it got soldered, there was a little solder bridge,
Mm-hmm.
and it wasn't supposed to be there.
I get that.
And those are kind of the most significant problems. Those are the things that kept reoccurring.
Right.
And so I made a little table, right? Because this is what we learned. We learned in
Yes.
school, you make data tables.
Yes.
You analyze the data, right? And so I took her the data, and I said, this is what I've discovered. I said, I think that somewhere along the production line, there's somebody over there who's got the wrong part in the wrong bin,
Uh-huh.
right? Or
Right.
they don't know how to put in the part because they put them in backwards. And she said, oh, you're probably right. Let's go have a look. And sure enough, we went out to she takes me out to the production line. She says, which one is it? And so I said hello to the people that are there,
Yes.
right?
Right.
And I said, I think it's that one. And so I pointed to the bin, and she reaches in, and the girl, right? She
Mhm.
reaches in there, and she pulls out the part. And I look at it, and I said, yeah, it's the wrong part.
Right.
And she goes, oh. And then she said, what's the other one? And I said, okay, so we went over to a different area, right?
Right.
And I said, let me see the drawing that shows you how to put the
Right.
parts in. And sure enough, the drawing was backwards.
Okay.
There's a polarity, and if you put it in
Right.
backwards, it doesn't work,
Right.
right? So, it was things like that, right?
Okay.
So right away, all of a sudden, the failures stopped, right? Now they're going through production, and they're coming out. Well, my supervisor was really happy with me.
Yeah.
And she says, but you still got to fix all those.
Okay.
Okay, so later I get to work with the engineers that are building the new prototype machine.
Right.
Right. Okay, so now I'm building the prototype,
Mm-hmm.
and this is a machine that didn't have a processor in it before,
Right.
and it's the first of its kind. It's going to greatly reduce the cost of building the machine.
Mm-hmm.
I mean, they're going to cut costs like crazy.
Right.
Most of the machine has got a lot of mechanical in it, and it's got a whole lot of electronics in it, and the machine is big and heavy. It's a bank teller machine,
Right.
and it's got this specialty printer that prints checks, and just big heavy machine, right? It automatically updates to a computer system, and it deposits money into people's accounts, and it's got a lot of security measures built into it, but just a big clumsy machine.
Okay.
And I can imagine that the service on it must have been high. It must have broke down a lot. This microprocessor that was coming in was going to make this thing so much easier to do.
Okay.
The cost of this machine was about to go down.
Shoot down.
Oh, less than half.
Okay.
Yeah.
That down.
Yeah. And the reliability was going to go up
Okay.
because it didn't have all those mechanical parts.
Right.
And at the same time they were doing this, they were also going to do what they call a point of sale terminal. So it's a electronic cash register. And so this is the first. Then they're going to build this other thing, which today is called the ATM machine.
ATM.
But this is the first of its kind. It's never been built before. It's the prototype. And so I worked with those engineers at putting together their prototype.
So everything was in front of you, like till the ATM machine.
Yeah. So this was. So I'm working for them, building these prototypes.
Right.
A machine that's never been built before, and we get it running. And then after we get it running, we have to redesign it.
Redesign it. Yes.
Because this is my first exposure to research and development. An investment group came in and told them what it is that they wanted. They wanted a bank teller machine that used the microprocessor. They wanted the point of sale terminal, cash register, that uses a microprocessor.
Okay.
They wanted to build this automatic teller machine.
Okay.
So because they knew that there would be a market for it. But no one had ever done this before. And so I'm building these machines that are going to be built for the very first time. This is research and development. Now, I'm not doing the research. The engineers are. I'm involved in the development as a technician, and I'm putting the pieces together.
Right.
And, of course, it doesn't work. And so then we got to do a lot of testing, lots of testing, test, find out why it doesn't work. Some of the errors are so subtle. Just little tiny things make a big difference. Some things are hidden so deep. I remember one problem that I worked on that just was so hard to solve. Static electricity would open the cash drawer on the cash register.
Right.
So if you were walking across the carpet and you went and touched the cash register, cha-ching, the door would open up.
Okay.
That's not good.
Uh-huh.
I mean, could you imagine someplace like, I don't know, your favorite department store, and it's Christmas time,
Right.
and somebody walks by, and all of a sudden the cash register opens up with the drawer in it with all the money? This is not good.
Completely.
No, this is not good. Well, we worked on trying to find out why it did that. We tried all kinds of things to solve the problem. I went to Caltech and I spent a week in the library just doing everything I could learn about static electricity. And we eventually solved the problem, and we had to throw a lot of tricks at it in order to be able to solve the problem. And once again, it was related to the fact that microprocessors and integrated circuits were brand new at the time.
Okay.
And, oftentimes you don't know what's going to happen to your machine.
Right.
The theory works fine. The real world, it doesn't work so fine.
Cannot rely.
No. The other thing that we find when we're taking and building a prototype is that this is not the way it's going to be built in production. Getting it to work for the first time is what we call proof of concept.
Proof of concept.
Yes, proof of concept. So we have a working machine, but we can't mass produce this. This thing has to be built by a technician and an engineer working together, and there's so much labor involved. You're not going to make a profit.
Right.
And so after we get the proof of concept working, that prototype then needs to be reverse engineered.
Okay.
So now reverse engineering comes into play, and we take a look at what we put into this machine, and just like we did with algebra, where we take an equation and then we simplify it.
Right.
We start throwing algebra laws on it and rules of exponents and
Yes.
simplify this equation to its essence.
Yes.
Well, we do the same thing with this prototype machine.
Okay.
We reverse engineer it, we take a look at it, we see if we can find an easier way to build this, to make the parts, right?
Right.
Throw some pieces away, you don't need them anymore. The idea is to cut down the cost of manufacturing. And if you can simplify it, then its reliability increases.
Okay.
And so another reason for reverse engineering is to increase its reliability. Especially for these machines. These machines are commercial. They're not consumer products. They're built to be run for a very long time without failure.
I get that. So mechanical engineers, do they also like innovate their own stuffs, like different kind of machines and all?
Well, working on this printer, one of the reasons why it was my nemesis, I realized, is that it's a machine that is a lot like, it is a robot.
Right.
It is a machine that is controlled by a microprocessor.
Right.
It has a program it's supposed to run. It's got electrical power that it needs to do its job. It's also running chemical because it's got to print somehow, and that chemistry starts to maybe cause problems. The printer is a very complicated machine. Okay. And then you have to be able to interface it to any computer, and so now you got all the software programmers that are getting involved. This little robot, any robot, right, is at least 6 or 7 engineering disciplines working together to try to create something.
Okay.
Yeah.
And so, as you just mentioned, 6 to 7 different disciplines. Do they even require 6 to 7 different engineers like
Yes. That? Yeah, there's specialists in each of their areas, but there also I was exposed to something else. The mechanical engineers were studying electronics.
Okay.
And oftentimes I would be asked to come in and do a brown bag lunch session, right? Telling them what it was that I found, because they wanted to hear it from a technician's perspective.
Yes.
And many times it was the mechanical engineers that I was there for. The electronic engineers, they already knew what it is that I'd been through, and what they made was a list of things for me to share with the other engineers on the team, so that way they too would know what kind of problems we're trying to solve.
Right.
So lifelong learning, boy, nobody does more than an engineer.
Okay.
And it changes every day. Every day something changes. So there's something new to learn. There's new discipline. You can grow your own disciplines. I've seen many of those mechanical engineers not only study the statics, how to build a chassis, the dynamics, how to build motors and gears, how to control those motors. So now you need an amplifier, and of course the intelligence that's going to run it. So now you need a computer. And of course, if you're going to do a computer, there's electronic hardware and there's a software program that's running it. And in the program, there's 2 different versions of that. There's what we call firmware, and then there's the application. And so it gets really complex really fast.
Yeah.
Any one person understand and know it all?
Okay.
Wow, that's a lot to know.
Yeah.
And that would be your senior engineer working on the project.
Seems a lot of reading. So, can you tell me just a small brief introduction, like what is the difference between a technician and a mechanical engineer? Like.
Yeah. So the technician might have a associate's degree.
Okay.
And they've taken 2 years at a community college. They've taken their general ed courses, and they've taken a lot of classes in this field that they want to specialize in. As a mechanical engineer, or in my case as an electronic engineer then. There's another field, it's called engineering technology.
Okay.
But the mechanical engineer would have to know how to use all the basic hand tools.
Okay.
Screwdrivers and wrenches and saws. Then you got to take it up another level. How to measure. We do a lot of measurement. both
Okay.
as a technician and as an engineer. You're taking a lot of measurements because in order to get that machine to run, there's a lot of calibration and alignment.
Uh-huh.
And so first we start with the alignment. You got to make sure that things are in the positions they're supposed to be in.
Right.
And then second to that, we calibrate for optimum efficiency and for its reliability. It's kind of like if you did the analogy of a car, right? Your
Right.
mechanic is a technician.
Right.
And so in order to get the car to go straight, after you put the tires on, oh, wait a minute.
Alignment.
Before you put the tires on, you've got to balance the tires.
Yeah.
And there's a machine you got to learn how to run, right?
Right.
And of course, before you put the tire on, you're going to do an inspection to make sure that the bearings are okay, that the brakes are all right, because now the tire's off is the time to take a look at that. And while you're looking at that, take a look at the shock absorbers and take a look at all the tie rod ends, all the mechanical pieces that could possibly wear out, because they do.
Right.
And as long as you got the tire off, now's the time to take a look, right?
Yeah.
Yeah. So this is the technician,
Okay.
right? Now, yeah. So then, and then as you notice, and now you got the tire on, right, and it's balanced, right, and so
Yes.
now you've got to do an alignment on all four tires to make sure that the car is going to go straight.
Straight.
All machines are like this, and they all need technicians.
Yeah, one of my car goes rightwards.
One of the things that I like to do now is I go over to the automotive schools,
Uh-huh.
and I ask them to introduce me to some of their very best students,
Okay.
and then I steal them.
That's a nice thing.
And what I do with them is I encourage them to, I say steal them, I don't really steal them, okay?
Yeah.
I mean, I just show them that if you're that good at being an automotive mechanic, you might want to consider a job that pays a little better.
Right.
Top pay for an automotive mechanic is about $70,000 a year.
Mm-hmm.
That's starting pay for an industrial maintenance technician, a control systems technician.
Get that.
It's got all the same skill sets, and but the machine costs a whole lot more.
Mm-hmm.
The machine makes more money than the car does on a day-to-day basis.
Okay.
So since it's part of a factory, if the machine shuts down, the factory shuts down. And
Right.
so they pay the technician a whole lot more to keep it running.
Okay.
So it's a job though that, like being an automotive mechanic, many of these jobs are very dirty. You know, you got to go in there and you're going to
Yeah.
take out an electric motor, and it's a 20 horsepower motor, and that's a big machine, right?
Right.
And so, and then in other cases, right, it's extremely clean. We're talking about level 3, level 5 clean rooms
Right.
where you have to put on a suit,
Uh-huh.
right?
Yeah.
Okay. I mean, people that work in there, they don't get sick because the air is filtered so that even the bugs, the
Yeah.
viruses, and the bacteria don't get in.
Don't get it.
Yeah, they're making medicine.
Right.
And so, there's all kinds of different places where this technician can find work. But, many of these technicians that have studied multidisciplines, so maybe they were really good as a mechanical technician.
Uh-huh.
Now they went ahead and studied electronics, or they studied electrical power. And there's a difference between the two. And maybe they did all three,
Yeah.
right? And maybe they know how to use the computer. Maybe they know how to do some computer configuration.
Right.
Well, now you've got yourself a control systems technician.
Control systems technician.
But you can see how the disciplines had to come together. There was a lot there to learn. It wasn't a specialist in one particular area.
True.
They might have started that way, but lifelong learning is something that every technician and every engineer has to embrace.
Right. So, like, there is, in any kind of project, there is a collective kind of like engineer or technician kind of stuff, not a specific field.
So what I see happening, especially with the students that I've trained,
Mm-hmm.
my alumni,
Right.
they go on to get an engineering degree eventually.
Okay.
About half of them do. About 50% will go on to the university and get a baccalaureate,
Wow.
and they'll do it in one of two different areas. Either they'll go and get some of them will become a technologist,
Right.
and others will go on to study the problem with the engineering schools is most of the curriculum is designed for research
Mm-hmm.
and development.
Okay.
And so it's theoretical based. And so they don't get a chance to put their hands on the hardware very often. And in some schools, they don't ever get a chance to actually build anything. It's all theoretical. There's a lot there to learn. I mean, it's a year and a half of mathematics. It's a year of physics. And then you get to do the engineering classes.
Okay.
Yeah, that's crazy.
That's
Yeah, it takes
Okay.
5 to 6 years to get an engineering degree.
too much patience for just touching the engineering point.
So